Welcome to EDU World Space.
Okay, so we need to take the following molecule. Take me a second to sketch out here. And determine whether the hydrogens indicated are, and I'm just going to leave that. That's a methyl group, right? I guess I could write CH3 for now. Okay, whether the relationship, whether these hydrogens are homotopic, enantiotopic, or diastereotopic. I find the best way to do this is to simply replace each one by one with deuterium, and then look at what the relationship between the resulting molecules is. So what do I mean by that? Well, I'm going to redraw this same exact molecule twice. In one drawing, I'm going to replace the upper hydrogen with deuterium and leave the bottom one as is. Okay, and in the other case, I'm going to replace the lower hydrogen with deuterium and leave the upper one in place. And then what you can use to answer the question as to whether the indicated protons were homotopic, enantiotopic, or diastereotopic is then say, well, what is the relationship between these two molecules? Are they the same? Are they enantiomers, or are they diastereomers? Okay, and what we'll notice then is that since they differ in the stereochemistry of both stereocenters that we've now created in this molecule. Remember, this was not a stereocenter before due to symmetry, but it is now due to the asymmetry that we've introduced in the molecule. What we'll notice is that these are, in fact, enantiomers of each other. And what may help point out that they're enantiomers is to redraw. I'm going to redraw the lower version of this, but I'm going to flip it onto its back so that we can more quickly see how it is that I know that these are enantiomers. So I'm going to basically turn it on its axis 180 degrees and draw the result. So the deuterium will now be up above. But notice then that would mean that the deuterium, if it's moving up to the top, will be on a hash rather than a wedge, right? And this methyl group, which was previously on a wedge, will now be on a hash. And then there's still just two hydrogens here, so it doesn't really matter if those are on a wedge or a hash. But now when we look at the relationship between these two molecules, it's probably a lot easier to see that they are enantiomers, or that they are, in fact, enantiomers, right? It's the same molecule, except for the deuterium, which we've now moved to the top, is on a dash, and the methyl group, which was previously on a wedge, is a dash. So if these are enantiomers, then that implies that these two hydrogens, which are the things we replaced one by one with deuterium to generate these enantiomers, must be enantiotopic. If the result of replacing them one by one and comparing them had shown us a pair of diastereomers, then they would be diastereotopic. And if the result of replacing them one by one and comparing them were that we got two of the same molecule, then they'd be homotopic. Okay. So the best way is to just redraw the molecule, having replaced each one with deuterium or another appropriate atom, and then comparing them to see what their stereochemical relationship is, and using that to determine the chemical environment relationship between them.